Let us look at complexes of a group. So one of the challenges is finding the subgroups of a group, all of them. So to figure out that, let's look at complexes of a group. Complex is any subset of the group, whether it forms a subgroup or not. Which means all subgroups of a group are complexes, but all complexes are not subgroups. The set of all complexes of G is the power set of G, written as P of G. Let's look at an example. Let's take the group of cube roots of unity under multiplication. We know the Cayley table. The order of this group is 3. So the power set of G will contain 2 to the power of 3 equal to 8 subsets called complexes. So these are the various subsets of the set G. We have 5, which is the empty set. We have a subset containing only 1, omega, omega square, subset containing 1 and omega, subset containing 1 and omega square, omega and omega square, and finally 1 omega omega square. So you notice there are 3 plus 3, 6 plus 2, 8 subsets. Now, let's filter this set, the power set. First of all, we remove all those subsets which do not contain identity. So here, the empty set doesn't contain identity. Omega doesn't contain identity. Omega square doesn't contain identity. Omega square doesn't contain identity. So we remove all of them and we are left with this subset of this power set. Remember here the identity is 1. Now we use closure property and the inverses to again filter out those subsets which are not closed and which do not contain the inverses of the elements of the set. So we are left with only these two. So in the power set of G, the subgroups are the trivial ones. That is the one which contains the identity only, and the other which contains all the elements of the group. This is a subgroup of G, and this is a subgroup of G. This is more specifically a proper subgroup of G. We have seen one example. Now let's look at another example. Complexes of addition modulo 4 of integers. Again, we know the Cayley table for this. So here G is equal to 0, 1, 2, 3. These bars represent that these are congruence classes addition modulo 4. The order of this group is 4. The power set will contain 2 to the power of 4, which is 16 subsets. And these are the 16 subsets. Again, we start filtering those subsets which do not contain the identity. And here the identity is 0, congruence class 0. So only those which contain 0 we are including. Again, using closure property and existence of inverse, we again filter it out. So we are left with 3 subsets. A subset containing only 0, subset containing 0 and 2, and the entire set. So here 0 is a proper subgroup of G, 0, 2 is a proper subgroup of G, and 0, 1, 2, 3 is a subgroup of G. Okay. Now let's look at set operations on these complexes. Let H, K, and L be 3 complexes of G. which basically means you pick any three of these complexes or pick any three of these complexes. Now, HKL will be in the power set of G. So let's look at union of complexes. It is closed in the power set of G because you take any two of these subsets. If you take the union will be there in this power set. So let's take omega square. If we take the union, we will get a subset containing omega and omega square, which is there here in the power set itself. Similarly here, take any. So let's say 0, 1 and 1, 3. Union is 0, 1 and 3. So here it is 0, 1 and 3. So we can say H union K is in the power set of G. Now H union K need not be a subgroup. When will it be a subgroup? If H and K both are subgroup of G, then H union K would also be a subgroup of G. So that is if and only if H is a subset of K or K is a subset of H. This we have seen in our previous session as well. Now let's look at intersection of complexes. It is again closed in P power set of G because H intersection K is a subset. Again, take any two. So let's take 1, omega and 1, omega square. The intersection will contain only 1. So which is there in the power set. Similarly here, let's take 1, 2 and 1, 2, 3. Intersection will contain 1, 2, which is there here, 1, 2. Okay. So if H and K are subgroup of G, then H intersection K is also a subgroup. Okay, so we have looked at union and intersection of complexes. Now let's look at group operation on complexes. So again, let's take HKL be 3 complexes of G. So which means HKL are in the power set of G. And now H times K is going to be in power set of G. Similarly, K times L is going to be in power set of G. And H times L is going to be in power set of G. So here, when I use the star to represent the operation, I mean the appropriate group operation. In this case, it is multiplication. In this case, it is addition modulo 4. Let's take this example, this cube roots of unity. So here, let's say H is omega square and K is 1, omega. These two sets, let's take. Now, what is the product of these two subsets? Omega square times 1 is omega square. Omega square times omega is omega cube, which is nothing but 1. So we end up with a subset containing 1 and omega square, which is the next one, omega square, 1. Like that, you can take any two subset, multiply the elements, and the subset that you arrive at will also be there in the power set. So that shows closure property of the power set. Associative property, H times K taken first, then times L is equal to H times K times L. Again, we can take up two subsets, multiply them, take the third set and multiply them, and again multiply them in a different order. The result will be the same. if H is a subgroup of G, then H inverse is equal to H. That is, for all H in H, that is for all element in the subset H, the inverse of that element is also in H. So that would be existence of inverse. And now here, H times K inverse, that is inverse of the product of two subsets, is equal to the inverse of the second subset times the inverse of the first subset. This is our inverse law. So what did we achieve? We saw that a power set contains all the complexes, and these complexes may remain complex, or they may actually form a subgroup under the appropriate group operation. And this power set satisfies closure property, associative property, and if we include only the subsets which are subgroups, then existence of inverse is also there, and the inverse law is followed. That was complexes of a group. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.